It would be nice if we have also a couple of people left in the audience, so I think that's enough.
It's very confrontation style.
Now fight. The two audience members can join. Okay, no, but I think actually this is very, very nice because this is meant to be a discussion, and a discussion as in every single person who is here is very welcome to ask questions and to also answer the different questions that will come around. And that would be also very helpful for me because I have 2 questions and we have 1.5 hours. So please feel free to also, as panel members or audience members, really come up with your own question and don't hesitate to speak up. So.
Sorry, just I think most of the speakers, we've introduced ourselves while speaking, but maybe we can have our audience members introduce themselves.
Yeah, that's a very, very nice idea. So I just have one small announcement to make. Thank you. Yes, because for the people online. So there is a huge audience which is actually online listening to us right now. So in this sense, the microphones are important, and also this session is recorded. So I think it's a very good idea that we each introduce ourselves, but right before that, I would like to make one small announcement, which is here behind us. So there will be a special issue of the Journal of Rheology. And of course, rheology is about anything that flows, so soft matter is perfectly fitting to this journal. And it's a special issue specifically on space application and low gravity research. So if you're working on any type of soft matter and it involves gravity or space environment, it would be really absolutely great to feature your work in this special issue. Deadline for submission is May 31, so keep it in mind. Would be lovely if you want to take part. Now I will start on my left, and we can each introduce ourselves one by one.
Okay. I'm the same of this morning, so I'm Stefano Buzzacro from the Polytechnic of Milano. I'm involved in the COLIS project, and I think I work on Earth, I work about soft matter in general, developing optical method for study soft material.
Matthias Sperl from Cologne, interested in playing with grains on the space station and on the moon.
Roberto Cerbino, University of Vienna, interested in soft matter and optics.
Gigi Cristofolini, University of Parma, involved in the emulsions in space, but in general, in soft interfaces in general.
Fabio Giavazzi, University of Milan, quantitative microscopy methods applied to soft matter and biology.
So I'm Anina Salonen from ESPCI Paris, and I'm interested also in soft interfaces and working on the FOAM-C project.
Alberto Vailati, University of Milan. I'm interested in the experimental study of complex fluids under non-equilibrium conditions and in general complex systems.
Jan Philipp Gabriel. I'm now at the DLR since 1 year, and I'm now interested in grains, in the dynamics of grains. And before I did a lot of work on measuring the dynamics of molecules and molecular system in all kinds.
Hi, I'm Jim Lisko from the Free University of Brussels. My interests are primarily in soft matter, in particular theory of non-equilibrium soft matter.
Fabrizio Croccolo, University of Pau in France. I'm interested in non-equilibrium systems, complex fluids, also thermodynamics with some application to CO2 storage, and of course, development of optical techniques. And I'm involved in some, I've been involved in other projects on the PlayStation, space station, and now currently co-directing the giant fluctuation project.
Thanks. So I'm Sébastien Vincent-Bonnier. I'm working in ESA-HRE in Naaldwijk, and I'm interested in soft matter in general.
Hi, my name is Tymoteusz Kraski. I'm from the Polish Space Agency, and I'm just an audience member.
The one.
What's your background? My background, not related at all and not technical. I work with international cooperation and strategy. So I'm here as a curious audience member again.
Ewa Zusnarska from Polish Space Agency. I'm also from Department of Strategy and International Cooperation. I'm also in PBHME committee, so connected with exploration. However, I'm here because the topic is really interesting and I just wanted to know more. And I'm quite surprised when I'm in front of everyone.
Hello, my name is Thomas Vogtmann. I work at the German Aerospace Center. I'm interested as a theoretical physicist in the flow of viscoelastic, viscoplastic fluids, and in the remaining time I put experiments on sounding rockets.
Hubertus Thomas, also from DLR Cologne. I'm working in the field of dusty complex plasmas, and I did experiments right from the beginning on the ISS. From 2001 with the plasma crystal project.
Yeah, hi, my name is André Mölzer. I'm from the University of Greifswald in Germany. I'm also working on dusty plasmas, and we are doing parabolic flights, and we hope to get a successor of the PKE experiments on board the ISS.
Mikhail Pustilnik, also from DLR Cologne. My background is dusty plasmas and plasma physics in general. And previously I've been doing plasma crystal 4 experiment on the ISS.
My name is Paolo Nibale. I'm also an audience member. I'm a physicist with an interest in imaging of biological systems. Right, thanks.
I'm Marco Braibanti. I work from ESA. My background is in physics, soft matter.
From behind.
To introduce yourself?
Oh, I'm just reporting for ESA. Okay. The organizing committee.
Okay.
Somebody's coming, so.
You can introduce yourself. Yeah, you have.
Okay, I'm Hamed Nirumand at Gdansk University of Technology, here in Poland.
Okay, thank you so much. And I'm Olfa D'Angelo from ESA-HRE in Toulouse, France, and I work on the rheology of soft matter and how it's influenced by gravity, in particular focusing on granular media. So I would say that we can sort of divide this discussion between scientific and technical questions, which I think we should start with, and then moving on to the more political questions of why and what for the future of soft matter in space. And starting with more the scientific and or technical questions, does anybody have something that they want to address? And if not, while you're thinking, I will continue a question that I wanted to ask to Anina earlier. So basically, we know and we've seen that the surface tensions of fluids is not a constant, that it changes a lot, especially with shear rate. is this something that you observe, / is this something that you think could be addressed by microgravity experiments?
Thanks. So anyone, feel free to chip in. So basically, so the question about the varying surface tension of liquids. So I think you're referring to, there are a few studies, one from Danielle Bond's group, recently measuring fluctuations or variations in kind of a dynamic surface tension as the systems are accelerated. And so there, whether we could measure it on the microgravity, how would this be? How could this help? I guess honestly, I'm not sure. So it could be. I guess. I mean, what could be interesting is it's always difficult to measure surface. Measuring surface tension is not so easy, and in particularly if you want to do. What you might want to do is to get these fast dilations. What could be nice is to be able to work with larger drops that you could then deform very rapidly, where you have kind of spherical symmetry initially of your drops, which then could help measure these systems. But that's the kind of possibilities I could see. But I wouldn't. Yeah. So I don't know if. Luigi, you have a.
I agree with your point of view. Just to establish a common language, I would say that interfacial properties is not characterized only by surface tension, but we should talk about the viscoelastic modulus of the interface, which in turn is a macroscopic description of something that on the microscale is probably related to absorption, desorption of individual molecules, or if you have particles, irreversible absorption, and different mechanisms drive the frequency or time dependence of this quantity. And so it's a very complex issue, many aspects that are impacting on the life of emulsions, or production emulsion and foams. And for sure, there is space for experiments in microgravity where isolated big and small drops can be manipulated more easily than on ground. So for sure, there is space for new science to be done in microgravity with this, without the constraints of gravity matching, because you can, of course, gravity match, not the foams, but the emulsions, but then affecting completely the chemistry of your dispersed liquids, and hence the diffusion of molecules in and out, for instance, makes a difference which kind of oil you have. It's an alkane with a CH alkylic chain, it will diffuse in a different way. If you have a silicon oil, it will be a different story. So there is indeed space for new experiments in microgravity, in my view, in my opinion. Thanks.
I have in mind another completely different of system, in the sense that we talk about mixture of colloidal particle and polymers, and the size ratio between the two particles is not too large. You can promote a phase separation between a liquid of colloids, in which one phase has a larger concentration of colloid, the other one has a lower concentration. And in any case, you can see them from a mesoscopic point of view like two liquids, and there is an interface tension between the two liquids. But of course, this interface tension is order of magnitude smaller than the interface tension that you have in simple liquid. And this beautiful work of the group of Lecker-Kerker and Dick Van Aert about that. And of course, in this case, if you're on Earth, one of the advantages, if you have a very small interface tension, you can have fluctuation and the interfaces are huge, but of course on Earth they are suppressed also by the gravity. So probably this could be a system in which in microgravity condition can be studied without the problem with the gravity, because the fluctuation becomes larger and larger.
But I think that has been done by Peter Liu and David Weitz.
I don't think that they are studying, but their system is at the moment is different, because we have the same collaboration with the ESA. But in that case, they are using a system in which essentially they study only the spinodal decomposition, evolution, something like this. I'm thinking on a way to measure the interface tension, the properties of the surface of this system. That, to my knowledge, is something.
A new machine and not just a Nikon camera.
Yes, for this system, for instance, spontaneous fluctuation of the size of the interface is larger, and probably you don't need to shear or apply any external field to see this fluctuation.
Question. So also for this kind of audience, I think is a nice question. So you say we do experiments in microgravity because we understand from the technical point of view, we remove gravity and we have an advantage. We can see something we cannot see on Earth. But can you elaborate a bit more what will be the applications of this kind of research in terms of space and in terms of Earth's benefits? So I see Matthias and Luigi touch a little bit on this, but I would like to, if you have some more insight about that. Who would like to?
Well, currently my favorite is concrete, which I showed briefly on the second slide. And there we find that for certain compositions, so beyond the headlines and certain additives, you find that your material is 20% harder than the same composition is on Earth. If you allow it to harden without the impact of gravity, where all those processes are then different. And one of the seeming reasons for that is that you allow the hardened, so we have a lot of bubbles in there, which is strange because as a materials engineer you wouldn't want that, but we seem to depose everything the hardening cement doesn't want into the bubbles, and then the holes in the system certainly don't carry weight, but everything else is much harder. And what we are currently trying to figure out is how can you reproduce that once you have understood the mechanism, that you put a flowing agents of some sort into the mixture to allow a ground-based cement mixture to have a rheology allowing for the hardening process and the rheology to compete just in the right way, that you have the strength enhanced, for which in turn you could then reduce the CO2 or the cement content, which is roughly linear. So this is a real-world application and also fits into mega projects of cement industry and science to get rid of the large impact of CO2 from the building industry. So if I try to gather additional money at DLR, I sometimes claim that if we make only moderate progress in saving CO2 in cement, we could do away with all the research on getting better airplane turbines because that's a lesser amount of CO2. So this is a real big thing, and a small incremental change by better understanding can help tremendously there.
May I? In my opinion, there are several ways in which soft interface may play a major role as enabling technology for space journeys. First, in the field food, so the production and conservation of food in microgravity. I mean, the life of an emulsion is completely different when you remove creaming, so understanding this and controlling this is a key step for food production, for sure. And more interesting to me is the application of solid foams. This is a project we are pursuing in the lab now, but it could be easily translated in microgravity. If you think of a solid foam made of a photocatalytic particles like titania, it offers the advantage over the normal photocatalytic filters of having a large amount of surface because the foam is intrinsically a high density of surface. You have tens of square meters in few cubic centimeters. And of course, you need to tailor this in terms of surface, of permeability, and of optical access of this. So there's many aspects that need to be controlled so that you can activate and exploit photocatalytic activity of a solid foam. But for sure, this would provide high efficiency, lightweight means of purification of air, and this would be beneficial, not of course on ground, but would be important also for long space flights. And so this is another direction in which I see direct application of what we are doing as enabling technology. Not exactly, because in the aerogel, you have a lot of surface, but you are bound to what it's happening to be the structure. You don't have nice control of this. And typically, by aerogel, you produce something that will break up in small particles that have an aerodynamic diameter that is, then it's contributing the pollution of the air, but it's not efficient as a means of purification. On the contrary, if you exploit a similar route for the production of this is what we are doing. We produce nanoparticles as an aerogel, then we how do you say? You isolate the particles and suspend them and use these particles as a complex with surfactants to stabilize liquid foam, which is then synthesized to form a solid foam. And by this means, by controlling the amount of solidifying agent, we have shown that we can control the average diameter of the holes and the mechanical properties of the object as itself, something that you cannot do easily on the aerogel. So this extra step is justified by the need of controlling both the mechanical properties and the viability or permeability of the object that you are realizing.
Thanks. So I think just one thing is also that in general, the kind of the basic understanding of the fundamental science often then leads into other advances in creating materials or into other applied applications rather later on in the process. And I think so understanding the fundamental processes of grains or bubbles or so on is, I think it's useful for a lot of products later on. So for example, I mean, quickly the sample I showed you, we saw the existence of these very small bubbles that exist for much longer than we expected. We now think that in material properties, as you, for example, solidify your foams, they might exist and they can really play a role in changing the properties of the materials, which of course, seeing as they exist also on ground, would have implications on the material properties. So that's something that I think is kind of directly fundamental science result that actually could have an application immediately.
So I want to say three quick things. The first one is about the experiment we were describing today, which is sedimentation. And I gave a couple of examples of processes in which we use gravity on Earth. So we give gravity for granted. And this is fine. You want to jump on the moon and shoot a nice video, but then at some point you have to live there if you really want to live there, or to Mars, or during the trip, or whatever you want. So what is the impact of the lack of normal gravity on producing products that we normally use? This is actually a very important question. Can we produce wine in the same way? No. Can we produce beer in the same way? No. So, and these are just futile examples, but very important ones. So especially if you have to travel for 1 year, I think you want to drink some wine, right, or beer. How do you do it?
We should have a topic, a team on alcohol production.
Exactly. And so our expectations sometimes are really wrong. For instance, in the Gradflex experiment, we proved that this idea that you go in microgravity to grow crystals and you get fantastic crystals, perfect and huge, is wrong, because it didn't take into account something that we didn't even know it existed. And we discovered it in microgravity, and we found an explanation of why you cannot grow good crystals in micro. So basic research, connecting to what you were saying, is actually sometimes, more often than not, also a good gateway to practical discoveries like this one. The second comment I wanted to make is about the ubiquity of soft matter in our life. So in the book by Roberto, there is this very famous incipit where a person wakes up in the morning and you realize, he or she realizes, I think it was a she, realizes how many soft matter objects you interact with from when you wake up to when you start to work. Toothpaste, yogurt, you name it. I mean, it's an infinite list, detergents and so on. So this means that soft matter physics, in particular, but not only physics, chemistry, soft matter is a very interdisciplinary field, mixing a lot of different competencies, from engineering to physics, chemistry, biology. And this brings me to the third point. There are many increasingly important processes in biology that are intrinsically physics. The most famous one is liquid-liquid phase separation. Now, if you talk to any biologist, liquid-liquid phase separation is the new thing. And this is a physics process that has been discovered by two physicists playing around in a summer school with samples and realizing that maybe that funny thing that they were seeing in a cell was equivalent to a phase separation in very boring, passive, inert soft materials. And now we are understanding that many of the organelles that we have in cells are of this type. They don't have a membrane. They're membraneless organelle. And they are very generic in the way they form because they form by a process which is not biochemical in nature, it's physical. So phase separation does not require a particular molecule to occur. And this is why nature uses it because it's a safeguard mechanism. Whenever other processes don't work, you know that this one will always work because it's a difference in some property, could be flexibility, could be length, could be whatever you want. Whenever you have an heterogeneity in some key properties of your system, there is a spontaneous tendency to phase separate. This is very generic, very powerful, and very bulletproof. So, and the second point I want to mention, because we worked a lot on that with Fabio, phase transitions in cell tissue. So, and this is the last thing I will say because I don't want to speak too much, but people have thought for centuries that, centuries maybe it's too much, decades, that if you have cancer, what you need to have is a cell changing identity from epithelial to mesenchymal. So basically a cell that decides that she or he doesn't like, in Italian cell is female, so let's say she doesn't like to be epithelial, she doesn't like to be social, she doesn't like to be in a tissue, and she wants to be alone. And when she's alone, she can go around and metastasize, okay? So this picture is old and obsolete. Now no one thinks that, not even the people who think that epithelial to mesenchymal transition is the transition, think that is one cell. Because we know from the Romans that if you want to be effective, you have to be a group of people, create a small phalanx, and then protect the interior and go around. So in the trip from the primary tumor to the secondary tumor, what happens is that many cells die. And so, and of course, if you are very unlucky, one of them survives and plants a secondary tumor. Now, what we are understanding is that this is one way. There is another one which is purely physical, which is very similar to when you melt a block of ice. You go from a solid where rearrangements are not allowed, like in a tissue, to a liquid where rearrangements are allowed, and there are collective motions very similar to the one in glasses that you see in this ultra-slow dynamics relaxation. Well, it turns out that this is very important also in cancer. And many cancers, in particular mammary cancers, use this way to disseminate. So my point, I think I made it quite clear, is that you cannot ignore soft matter if you want to understand this thing, especially because we don't know how these bioprocesses will be in microgravity. We never lived there. We never lived on Mars, we never lived on the moon, we never lived for 1 year on a spacecraft. I mean, some people did, but not so many. So we don't have information about how these processes, which are purely physical, are influenced by gravity.
I think there was another comment maybe on the same question. Or?
Yes, but if you have to comment, I thought it was very nicely to attach to it, but it's not. Yeah, so because I had a technical question in mind, but it connects very well to what you just said. Actually, I was discussing with some of the people at the coffee break about this liquid-liquid phase separation in cells. Because I'm now a biologist. I'm here on holiday, trying to refresh a bit of my physics. So what I saw in the session today was a lot of light scattering, which in a system, in a soft matter system, as the interior of a cell, is unfeasible. So in order to bring some of these measurements inside more complex systems, smaller length scales, I mean, what are ideas on the floor? And the specific technical question I had is, would a method, for example, such as fluorescence correlation spectroscopy be a valid replacement for dynamic light scattering or not? Thank you.
So very briefly, the things we showed you in our talk, this DDM, is using a microscope to do dynamic light scattering. So you don't need to take new data or replace anything. You take a normal microscope, you take a movie, a time-lapse movie like the one you would analyze in other ways, and you analyze it in a different way to get light scattering information. Well, yes, because you don't track the objects. You look at the fluctuations at the different Qs, and those fluctuations may be convolved with the transfer function of the microscope. This is, of course, unavoidable, but still you see changes, and you can pinpoint those changes at those length scales to the information that you're interested in. Just to make an example, with Fabio, we published very recently a paper where we measure the size of proteins, 2 nanometer proteins, with this method. Of course, we don't see the individual proteins, but the fact that they move, like in dynamic light scattering, gives you access to indirect sizing via mobility. So you need to have a model, but it is not different from fluorescence correlation spectroscopy, where you see the mobility of your molecules on the size of the beam. So it's exactly the same process. You never see the individual molecules. You see the changes in number inside the volume, illuminated volume. And this change is only dynamics. If you freeze your molecules, goodbye. Also in fluorescence correlation spectroscopy, there is no information there.
Yep. If I can add, I mean, you can use this approach. Sorry.
No. Just finish.
Which can be used also exploiting selective tagging of specific structure. So in a cell, you cannot see the scattering signal from a membraneless organelle in the nucleus and separate this contribution for all the stuff you have in. But if you have, for example, fluorescent tagging of a specific protein, then you can use this kind of scattering with images approach to get information about that specific structure. So you can do something like a scattering experiment using fluorescent microscopy data.
To close. So coming back to the general question addressed by Marco about the applications related to this kind of studies, complex fluids are present in living organisms, in geophysical systems. They will be present in the destination on long-term space missions. And as we outlined in the presentation, they will be important. Their processing will be important during long-term space travels. So a very wide general fundamental problem, but directly related to the applications, is the understanding of the stability of these complex fluids in the presence and in the absence of gravity. Because in principle, we are investigating fluctuations in complex system, and it's generally assumed that a fluctuation, usually people are accustomed to equilibrium fluctuation which relax back to equilibrium. In non-equilibrium system, this is not the case. A fluctuation can get amplified due to the non-equilibrium condition and lead to a catastrophe. So for a typical example are convective processes on Earth, which are started by very small fluctuation, which give rise to a symmetry breaking, and then you generate convective heat and mass transfer. Convective heat and mass transfer might be desirable or not desirable. This depends on the specific application. In some industrial applications, you require them. So you need a way to control them, but not only on Earth. The experience on Earth is very wide. So what you can do, as Roberto said before, you can go to microgravity and say, okay, I have removed gravity. I have the perfectly stable system. Graphlex has shown that this is not the case. You have large amplitude fluctuation, which extend up to the size of the container. And again, if you go under different gravitational conditions, I mean, the answers are not there. We still don't know exactly. If you have an instability, this can lead to a phase separation of the system. And so what can we say about the shelf storage time of the materials that we need during the space exploration? A typical example of this is represented by the fact that in our project, in the Giant Fluctuation Project, we have an industrial partner which is very interested in the understanding of the stability of protein solutions. Protein solutions are used for as a substitute of chemical pharmaceutical products because they are more compatible with the body. And it would be very important to understand the long-term shelf life of these protein medications during space travel in general. So again, the topic is a very fundamental one, stability of a fluid in relation to the presence of the absence of gravity, so not stability against aggregation or chemical. But again, the connection with the industrial application on Earth and the success of space missions is very close. I mean, if you understand more about the stability, you get benefit on Earth as a return which will guide. Of course, the time to go directly to application can be not so short, but in the case of this industrial collaboration, we have a very strong connection with the application as well.
Yeah, if I may, basically Roberto already started answering what I wanted to touch upon, because I think it's a very exciting development over the last decades that soft matter physics on ground has undergone, that it has looked more and more into biology, into understanding, as you were saying, the physical processes behind a lot of stuff that biologists previously thought were kind of complicated things encoded in genes and whatever. Yet if I look around here, there are also people here who do human physiology in space, who look at microbiology in gels, but it seems to be very separated still from the soft matter discussion that we're having here. And it's also an experience that I have with the German Space Agency, that they're basically the soft matter people and the material science people on one side and the bio people on the other side. So I was wondering what we all think, where could we cross-fertilize, where could we find exciting topics to join these two camps, where can the soft matter people directly attach to biological research that is being done in microgravity. I mean, Roberto, you already mentioned an idea that I also came up with, but maybe there are more.
Okay, another thing that I think is important is that in many cases, the soft material that we study are not important per se, but because they mimic the behavior of other material. People usually, the paper of Wilson Poon that says colloid has big atoms. And now that you have a patchy particle, you can say probably also that colloids are molecules. What doesn't means that in many cases, soft materials are useful because you can study much easier properties of other material. Imagine of crystallization is much more easy to see a crystal of colloidal particle in which you can follow the dislocation. And essentially use colloidal particle because they are big and they are slow. But one of the consequences of this is that they are soft. So when you want to mimic the behavior of a really hard solid, in one case, probably the gravity is irrelevant. If you want to study how to destroy a piece of metal, is not the gravity is a very third, fourth, fifth order correction. But if you have a colloidal metal, if you want something like this, here the gravity is important. So to be able to use microgravity in order to have a condition that is much more similar to other material could be really, really useful. And I mind one of the experiments when I work with my gel, one of the way in which they are extractor is due to the fact that during the solidification of this material, we store inside this material stress. And the way in which you store the stress in this material, of course, depends on the history of the material, the thermal history, if we are on Earth, if there is convection or not in your material. And what I saw is that, for instance, for some of my gel, this structuration is a series of sort of quakes that resemble the earthquakes, in some cases with the statistics. But what is the problem is that, of course, my gels are soft, so I cannot avoid the presence of the gravity that slowly compress the material. So the evolution probably of the gel is not an evolution without an external field, but it's like you are making a very, very slow compressing experiment of your gel. And one of the most recent result that surprised us is that in this material you have two kinds of, if you imagine earthquakes, in this case it's gel quakes, in which you have small localized quakes, but at a certain point you have a macroscopic, it seems a sort of microscopic failure of the material. That's, these earthquakes span all the size of the gel that on Earth we are talking about centimeter, the whole size of the sample. And what was surprising for us is that when you have this macro event, first of all, they are not random in time. If you talk, people think that earthquake you cannot predict. In general, it's true, but there are some specific earthquake in some region in which, for instance, if you live in I don't remember the city in Japan, it should be a nightmare because every 7 years you have an earthquake. And so clearly the mechanism for this earthquake is general, is different from other kind of earthquake. In our sample, we saw both the populations of big earthquake with a specific timing and a random in time smaller earthquake. But what is interesting is that before the macroscopic earthquake, you have a sort of precursor of the dynamics. You can see that something is happening. And this is, I think that now people start to saw also in other material in which we apply a stress on this material. And before the rupture, you have some indicator, what is called a plastic precursor of the failure of the material. So I think that I don't want to say that we will be able to predict earthquake because it's too much, but especially if you have material that are really heterogeneous. Now from an engineering point of view, my formation, I'm an engineer, you say, okay, I have a no ring and I know the statistically the rupture time is 10 years. It's better for me to change every 5 years. There is something that maybe is easy to do on Earth, but when you go to Mars or somewhere, you could have also problem of logistics. Simply to say that instead of changing something every 5 years, you can change every 7 years, because locally you can know if something is happening and anticipate the rupture could be something that is important for space exploration.
No, I wanted to answer the question of Thomas. Okay. So it's a difficult question, but a very good one, of course. What I can tell you is that in science, we're slowly fixing this by interdisciplinary. So the question was, I remind the question, what can we do to put physics and soft matter physics and biology more in touch and to do things together rather than living in our isolated and sad lives alone? If I rephrase the question correctly. And in science, we're trying to fix this in many ways. Collaborations, I mean, if you see many of our recent papers on the topics in the author list, which is very long, there are engineers, biologists, physicists, you name it, mathematicians, and so on. So research is intrinsically and increasingly becoming interdisciplinary. This, you see it, especially if you look at the so-called big journals like Nature, Science, Family, and so on and so on. In conferences, the same thing. We are increasingly seeing, for instance, EMBO is a biology group association, and they organized meetings lately where they had a physicist and a biologist having a joint talk. And the physicist was always a soft matter physicist. So this demonstrates that when we manage to do that, this works. And then I have to say something to our ESA friends, because if we, for instance, form a facility definition team which is called soft matter and biophysics, but then the representation within the team is mostly soft matter and there are only a couple of people who do biophysics, that's a political decision that has to be made. How important is the name of an object? If the name of an object, which could be a facility definition team or any other thing, is important, then the content of this object must match the name. So this will be one way within our community to improve these things, to create objects in which not only in the name there is biophysics, but also so by putting in the name is a first good step. But then the second good step would be to keep up to the name and to really make it half and half. I know it's challenging, but this would be a first way. A second way, we discussed this with Sebastian and Marco for sure, and also with Pepe, would be that ESA starts to organize sessions in conferences, for instance, in soft matter, kind of forcing this if this is interesting for ESA. And this maybe also in the other ESA part, the biology, start to do similar things just to merge the two communities a little bit more, like we do in science. Because in science, we do it. In science in space, not yet. But science in space comes always later, so this delay is fine, I guess.
Here it is.
Oh, that's this way. So I have one comment from actually the question that was from Marco about the application, and also I would like to follow up on actually your question because so the comment was on the application side. I mean, you listed, of course, a lot of applications that are directly linked with the research in soft matter. But on the other hand, in terms of benefit, this is not like you have, because this question, I don't know if it was your idea, Marco, is also because very often at some levels, even journalists also are coming to agencies like ESA or any, probably to you, and say, okay, what are the benefits for the citizen? And usually what they are looking for is something that is available on the shelf that any citizens will see and say, okay, you are working on colloids, but does it make the coffee better? Does it make the face cream or a bit better? Something like this. And of course, and I think this is okay. Most of the research you are doing is not immediately, you don't have necessarily immediate benefit on that. I mean, also on foam, you have food industry that are involved and everything, but this is not like you say, okay, this chocolate bar has been improved because of the space experiment you did in 1999 or whatever. That's not the case. So, but I would say we could be also quite relaxed on that and say there are applications, but there is no immediate benefit, and so this is indirect. So just a comment. And then I would like to follow a bit your comment on, and maybe put it a bit more general. We had nice talks about foam, emulsions, colloids in general, and then I think, Roberto, you mentioned one of the Nobel Prize. It was Perrin, but it was in 1929, right? You didn't mention De Gennes, but also it was not that young. What will be actually in this field of soft matter also the field where we may have the most benefit? And I think it was also maybe behind your question is it looked like also what Roberto was mentioning when you are talking of maybe a cross between physics and biology, maybe this is where you have some sweet spot where we have. And that follows also your question, because if it is the case, then, of course, the name of what you call a facility definition team, but this is just an exercise or even a facility, of course, the name is important. But the name has to reflect also the strategy and the priority. So if we think, you guys, because this is a top-down approach, if you think that biophysics is the best, bottom-up approach, yeah, but sorry, a good point. But if it is also what we hear that biophysics is the best, of course, it should be named and also translated in the composition and everything. But this is also an open question for this forum. Where is the strategy? Because also in terms of funding and everything, of course, what we want is to go where you will have the most rewarding research in terms of outcome and everything. Not that incremental research is bad, but the priority is important. Yeah. Sorry.
Thank you. So I wanted to make a comment because for me there is also other applications of soft matter. So Matthias first mentioned the CO2 reduction in cement production, but there is also CO2 storage. For example, polymers are used to the so-called solid storage of hydrogen, which is a very important application for energy sector, which... yeah.
Now, what I mean is that I agree, but it goes along. Maybe Anina could have said something on food and everything. The thing is that if you are very careful and you say yes, it helps CO2 sequestration. I mean, how much ton of CO2 is done today is sequestrated with that? So you see the point. And then if you go to public, then you have to be very careful because if you claim this is for that, fine, but you need numbers. And okay.
Yes, but the application to the storage of energy by hydrogen is something that is for the future and is very important, can be very important also for space exploration. So it's another subject. It's different from CO2 capture. Okay, it's another thing, but can be very important. Just to say that soft matter has applications in very different sectors.
I have a comment on that probably open another possible question is related to the fact that maybe we should also change the way in which you think the experiment of the space station. What I want to say, if you look this morning, the people that talk has a strange combination of people that is able to build the instrument and make the science with the sample that they decide to use. That is quite unusual. There is not so many, especially if you move away from the soft matter community, the people that are able to know in detail the technique, how to build a correlator, the electronic, everything that was asked to us to build this instrument, and at the same time to be able to understand the experiment that you are doing, the material. Especially if you move and you want to collaborate with biologists, the knowledge of the instrument by background is completely different. You cannot imagine that there are biologists that decide to build an instrument that is nothing more maybe than a microscope or something that you use in the lab. And this is, I think, a problem. If you look at, okay, I'm Tokyo College, there is a special case, but we take 20 years from the proposal to 21, because the first experiment will be in the next year to develop this one. And I'm looking at the experiment, the instrument that was discussed today, and my question is, but we really need all these instruments, or if you want, at the moment, the idea is, I have a physical problem, and typically we build up an instrument that solve this problem. Then I arrive 5 years later and say, okay, I have another soft matter problem that we build another instrument. If you look on Earth, it's something that we discussed with Roberto and something like that. If you consider light scattering, microscopy, and rheology, maybe you cover the 95, 98% of the experiment that you can make on Earth about soft matter in general. So the point is, in the future, I know there is something we can discuss later, it's not better to have a light scattering facility, not standard, not by a Malvern or any standard instrument, a microscope that is able to be modified in order to use all the technique that combine imaging and scattering. And the only thing that you have to design is the cell. So if you need to shear the cell, if you need to change the temperature, with the cell is a huge instrument. I think that if we sit there and try now 30 years later to repeat all the experiments that we discussed this morning, thinking that we have to use more or less the same instrument. I think that 95% of the experiment is still feasible. I don't know, maybe people doesn't agree. And I think this is not important only for soft matter community, because maybe this speed up the upload of a new cell, but also if you have to work with biologists, that they know that there is an instrument and maybe they can contact someone that is more from the soft matter side. They say, I have this problem, it's possible to collaborate on that, because they have to start from scratch to think something that is related to soft matter using instrument that come from the soft matter community is a huge barrier for biologists.
Yeah, I mean, you touched upon a lot of topics that are also very dear to me, because with what we do on the sounding rockets is very much driven by what you describe. Much more experimental than you can be on the ISS or so. So I want to answer yes, of course, and no. Because first of all, I think this very specific mix of people that you described, we need them, and we need to actually breed and educate people, like people who can be very deep in the details of a technical apparatus and also have the broad overview of the science that should be done with it. Because after all, doing experiments in space it's a very unusual environment. So a lot of our intuition fails, and you need the expertise of people who have both. And I think that there's a lot of problems in trying to separate, like into one who handles the technical aspects and one who handles the science. But then, of course, you're also right, I think, and it's something that in the FTT we've discussed a lot, that a more modular approach, a more standardized approach will help speed things up. And you get there with a certain level of maturity. So to make an analogy, I think in around 1900 or something, when the first driving licenses for cars were introduced, it was part of the exam that you had to do, that you were able to disassemble your car completely and put it back together again. Now, if you go to the average car mechanic, they will say, I don't know, I just replaced the chip and that's it. So that's, of course, the maturity of the system. And I think the same happens in the instruments. The first who builds a light scattering experiment to fly into orbit, you cannot take this approach of saying, I just give you my sample and then keep my fingers crossed. But maybe we are there now with all the work that you've been described, that has been going on over the past 20 years, that we can think of something more standardized and ready to use for also people who are not in the technical details.
So, but now he's back. So I just wanted to reply to you. You forgot Parisi. I mean, come on. So I know you want to sell us as old, but we're not that old. And the other thing is, the other thing I forgot. But no, you said something about applications. So I don't think it's 100% true what you say. For instance, we cannot tell you that we collaborated with a very important multinational company to solve a very practical problem on a very well-known product that was due to sedimentation. They changed an ingredient, the sample was phase separating, the bottle was not transparent, the person using it was not aware of the phase separation, the active principle was at the bottom. These things we do. Sometimes we cannot even talk about them, sometimes we can. And in other cases, the things we do in space, like all the things you have seen today, they have an immediate repercussion, maybe not on a specific product like a coffee bean, but Nestlé, who produces coffee beans, has a research center in which most of the people are soft matter physicists. And they optimize the ice cream, they optimize the coffee, and they optimize the foam, and they optimize everything. So what do we need to convince you that this has many applications? I mean, I don't know what to do, because it's actually everywhere.
Yeah. In that case, there were in some of the FOAM-C project officially, and there is no problem. The thing is that most of those industry are there also. I have some other example of industry that were there, but whatever, they were there just exactly. in Eco Japan also with you, but they are there just because they want to understand the process and then they apply it to their industrial processes. And actually, this is the strategy of many industry. So they are looking at what is happening on the, maybe reading your paper without you knowing and using your result and applying that in their process. But if you go in the route saying that this has some application, usually you need a concrete example and numbers, let's say, that really prove that. And this is really difficult, and sometimes this is not directly the case. But yeah, I forgot about the Parisian, sorry. Yeah. But it is, yeah, I don't know. Yeah, glasses. Yeah, also French.
May I? But,
I would have liked to pick you up on your misspelling of bottom up and top down. Because there's a big part of ESA working top down, formulating a problem, yeah? And then you typically have the problem not is the problem interesting, but is somebody going to die if we solve it or not? Yeah? So we have a problem with O-rings. Is that academic? No, it's not, because people died. Is the foam insulation an academic problem? No, people died. Now, how would you, and Angelique and Daniel showed that in the introductory speeches yesterday, how are you able to come up with problems that help us help you and help us financially to do it? Yeah, so how would you come up with top-down things you want answered from what I would say is your community? Do you know what you need, or are all our problems non-lethal?
Yes, there is a kind of list, but again, some of them, those technology are very boring because they are really technology that need to be ready in something like few years. And this is about propellant management, it is about shielding materials. And again, with the spirit that we know more or less what we want, it is more or less existing, the idea is just to verify. And so that's why when you go into maybe the more academic research, it's difficult. You have also in life support system the problem of multi-phase flow or transfer of mass transfer in general, gas, and so that could be related also on the topic that are addressed here. But very often they are very, very practical. So you have a multi-phase flow. Today we are using some filtering system, so with just massive filter. How could we increase by 20, 50% the efficiency of the filters, or using less of those filters, or having a system that is... So that's really the... If I take the example of filtering in a life support system, so we had also some few research projects, but they are in the pool of research, more the bottom up in that case. So this is
CCF, for example, capillary flow.
Yeah, no, we have other techniques with acoustic. Okay, acoustic that trap whatever you want to trap with, let's say, solid acoustic waves, and so you can trap stuff. The first question we have from the engineers are, what is the efficiency? How much? Very practical question. How much you can use this system? What will be the force? What will be the capability? And then, if you give this, then they will tell you, okay, this is better or not of the technique we have, and if it improves significantly the efficiency and decrease the risk, then that will fly. But yeah, you have some topic a bit like this, but again, they are very, very practical and engineeristic. Yeah.
Sorry, can I? Okay, I have 2 points. One is to answer to your question. So I think that it's difficult to foresee the application of the science we are doing now, but you can produce examples of applications that are there now from the science that was before. So, for example, Nespresso coffee is the good example of years of studies in soft matter that produced the benefit, and the benefit is the money is doing Nespresso from this. I mean, it's of course the business and the fact that we are happy to have, I'm not, but okay, if you are happy to have that coffee. So that is, there are many examples on that from past science that is applied to nowadays products. So from soft matter, so the tooth of, I don't know, the ice cream, industrial ice cream, or and many other things. The other thing I wanted to reply to Stefano's comment. And actually, all the things that you said are actually the things that we have been doing in the facility definition team. So we have tried exactly to go into this direction. I think there will be more a speech by Roberto later today, if I'm not wrong, that will show how we would like, 2 talks. At 2 o'clock. So sorry, I didn't remember the time. And that is exactly the way we are thinking the experiments after the International Space Station. And hopefully we will get into this direction. Thomas?
It's a fast replay was the provocation. How we can ask to Nestlé to funding ESA. And I think one of the problem is if I go to ESA, I say, Colis is perfect for you, but you have the result in 20 years, you don't have the money. So all the paradigm is you have to funding soft matter in general because maybe not Colis, but every year there is something that is useful for you, and ESA is able to make experiment that you cannot do in any other situation. So is a sort of like Netflix in which they pay a value equal each year independently of how many movies do you have, but because they know that at the end they have a result that they can use, or you have to find a way in which if I have an idea, at maximum 2 years, I should have some result. Because there is no other. When I go to the company, I'm in a chemical engineering department. My colleagues has a lot of money, but they make molecules, and they have molecules they can study in a standard way because they have to characterize the material and not anymore. But people start to want a result in 6 months, 1 year. And this is the typical, if you're lucky, maybe 3 years because they pay a PhD, but they want a result as soon as possible because it's clear is a problem. It's difficult to say to Nestlé comes in another ESA project because the first result is in 20 years. I think it's impossible.
In that case, it took 20 years. For 20 years, we had Nestlé in the
Yes, it is.
Financial involvement from their side, that financially, some of the teams were
Yes, but it's different. They funding the team, or the point is if you want that is the committee is no, but the idea is if you want a sponsorship that is not simply related to the fact that also I have a company that is interested in gel in general, and if I have a result on space, they are happy that they can apply, but it's a different funding scheme, I'm thinking.
And if I may add to that, I mean, as a theoretical physicist, I've learned to be very modest. So this idea of saying, okay, let me sit down and understand the process theoretically, and then I can tell you, big company, how to do things, this is never going to work. And maybe also the fundamental scientists saying, let us understand what happens without gravity, and then we sort things out, and this will help you. I don't think it will, because a lot of application is in process development, and as long as processes happen with gravity, there will be some empirical model, some simulation, whatever, that optimizes it right away without going to the space station. So maybe that tells us that we need to set up projects where the microgravity data points are a very beneficial addition, but where the project itself also rests on ground-based research that is embedded into it. And then you can also avoid the problem with the timescales and so on. And again, I like the chaos of this discussion, by the way. I mean, this joins back to where should we be looking for what kind of projects. And I think also in terms of selling to the public, if we accept that we do want to go to Moon and Mars and places, then the idea is saying, okay, let us understand on a very fundamental physical level what happens to the membranes of your cells if you expose them to microgravity conditions. That is, I think we can do a lot there with very simple-minded and robust experiments that also, I don't know, have some obvious relevance. Yeah.
I'll be quick. So I have 2 comments and 1 question. So one comment for Stefano, I think have been discussed, and I agree with you. 20 years to make an experiment is not a very, wouldn't call it a success. So with FDT, we are trying to make, exactly as you said, something standard, and well, you name it. You say light scattering, microscopy, rheometer, that's what came out from it. You're not surprised, probably. Yeah, we want to make experiments every year, every 2 years. I think that's the goal. Yeah, we are working on that, at least. Second comment is about, I think we should be careful a little bit with talking to the public. I mean, for sure we have to say about applications, but talking to the public could lead to the presentation we had, something we have seen already, where you have nice music and showing off rockets starting from Mars. I mean, I think that we shouldn't go there. And let's talk about, in technology, we have TRLs, right? So we don't go to an engineer and say, I want this tomorrow. We start from TRL 1 and you go up to TRL 9 and you develop it. And I think it's a bit too much to ask them. You do an experiment in space, or what are the applications? Or we have a mousse au chocolat made in space. I think this doesn't make a lot of sense. I know we are asked that, but I think we should push back and say, okay, now we do research. So we start from, we learn something new, cannot be applied tomorrow, but we are this is SRL, Science Readiness Level 1, and we are building up. The life support system is not coming tomorrow, but we have something new that will make probably the difference, but we have to work from there. So I think we should make this point. We should have to have examples, I agree, but that was my comment. And the other question I have to increase the entropy of the discussion, it was something that Alberto said at a certain point. We need to understand liquids or soft matter in microgravity, but you also said in different gravities. And so I have a question to you or to the audience. It was, so would be interested to have other platforms other than the ISS, but if, for example, the moon would be interested in doing experiments on the moon, and moon gravity or Mars gravity or other different gravities to really understand. So now we have 2 points, 0 and 1, but would be understand to see what happens in between. So it would be interesting in having some platform like that, for example. We have parabolic flights that are at moon gravity level or Mars. Oh, that was my question. I think Luigi was first.
Thank you. Oh, maybe. Please.
No, go ahead.
Okay.
Well,
okay. So, continue on what, I agree with most of the things that Marco was saying. First of all, industries, except IBM, Nestle, a few, most of my experience, at least with Italian industry, is that they come to the academia when they have a problem to be solved in 6 months. They may pay the amount of a PhD, but they don't want the result to take 3 years. It's difficult even for them to understand that it takes 3 years to give the answer, unless you give a quick and dirty answer. And they are happy with the quick and dirty quite often. So this is just to say, okay, we have to do it. We have to interact with engineers. We are not engineers ourselves. We have to interact with the industrial partners. And except IBM, Nestle, most of them are really not interested in the long-term research. Even our experience with Nickel is excellent. They are very happy to provide us surfactants. Honestly, they are not, if I'm honest, they are not calling me each morning to know the latest news. We are very happy to have them as partners, for sure. And this leads to the next step. So when we plan our research, of course, we're driven by curiosity, first of all, good scientific questions, but also I think it's part of our planning to envisage applications and do, I'm doing, for instance, again, come back to the example I know better. I want to do an efficient photocatalytic filter, then I have to understand better solid foams and start from liquid foams, solidify, synthesize and measure bed area and permeability and so on and so forth, because I have this application in mind. And this comes to what could be the role of the agency, not to come with questions for for very high TRL level only. Of course, these are very important, but also maybe to formulate, not to leave to us to imagine, okay, for going to the moon, we probably need better filters, or we need a sedimentation system that is more efficient, energy efficient, than a filtration system that would do the same, but with clogging and all the problems, but could also help us in defining long-term, low TRL problems, which are deserving our efforts and public money, because the question is to justify the big expense of public money that we are asking for.
So answering directly to Marco's question, I hope you were on the receiving end of our multiple submissions for the lunar parabolic flight recently. So there we argued that you have an additional data point with 1/6 gravity. Hydrodynamic instabilities change. Maybe you have even nonlinear stability stuff. And we go as far as direct efficiency of transporting bucket of grains from A to B, yeah, seeing if that works as intended or if there's some problem we have overlooked. So there's quite a number of things that can benefit from additional gravities.
Maybe I can jump in and actually answer this. So yeah, coming from granular matter, the interesting thing is that all the laws that are used in industry, in construction on Earth, are basically empirical. And if you try to say, oh, we can easily test them in hypergravity and then look at how they scale to low gravity, eventually they break. And the thing is, because we don't have those points between 1 and 0, so to say, we don't know where they break, and we can only imagine why they break. So for granular matter research, yes, everything that is in between is exactly what we need.
So coming to your question about altered gravity, as it was called yesterday in the introductions, I think that we have to separate two problems. Performing some science in altered gravity conditions can be done in LEO, with a very reasonable investment due to the proximity of the platform, by using a facility similar like the Flumius one. So once that I have microgravity condition, I can mimic very effectively the altered gravity, hypergravity, or whatever. In practice, we will never do this. I mean, now we are thinking about the soft matter facility, which does not contain this opportunity of changing the gravity level as a base feature, because there are some priorities. So the other approach, which was widely discussed during the strategic retreat at ESTEC, was how do we take advantage of the features of the destinations of space exploration? This is another thing. Once that I'm able to go to the moon, beyond investigating the moon, I can take advantage of the fact that the gravity is 1/6 of that on Earth, and establish a laboratory, a lunar laboratory. In the effort, we propose to have a facility dedicated to soft matter, specifically, because it would be very important. So the two things go along very separate channels. One can be done very quickly and requires a moderate investment, and the other one, in principle, Terra Nova 2030 promised to have the humans on the European humans on the moon by 2030, but I mean, 2030 is approaching, and this probably will come later, yes. Yeah. And also related to the thing that Stefano was discussing, the approaches are very different. We will discuss further in the FDT. If we want to involve a wider scientific community, I always see the same faces since several years ago, and there are plenty of scientists working on soft matter. We have to lower the level needed to access. And we already discussed this with some of you, but this can be done only by changing completely the paradigm leading to the access of the project, and this is strongly related with the ITER, which a project follows. And Nina some time ago raised some concerns about the ethical aspects in space experiments because they cost a lot of money and they give rise to the pollution on the environment, but also what I can do with the same amount of money on the Earth? The same amount of money would be twice or 3 times as much the money for an ERC grant. Probably I could produce a huge amount of science. So the thing that we have to dismantle and then reassemble again is the fact that we need faster times at a cost at a much smaller investment. And this again involves a very direct involvement of the scientists, the ability of the scientists to contribute to the realization of the prototypes and so on. And also, this I already discussed with some of you, but open the hardware and the resources generated during space research to the wide public. Again, there is a misunderstanding here. This is not a chance to leave the profit aside. If you open a market in this way, you find other chances of profit which are not there. The profit now is entirely of the aerospace industry, and ESA is there to distribute money to the aerospace industry. If you go to do the open hardware solution, you trigger and you have the synergy of several scientists in the world which can contribute to the project which you have devised, proposed solutions, and this can be done in a very fast time. But this would require, again, to dismantle and reassemble several of the concepts that lay the grounds of the base space research now.
Okay, Roberto, one last word, and then we will close the session.
So I wanted to finish with a question to you, which is the following. What you said could be asked to any other group here today. And I think the answer will not be more encouraging than with soft matter. I think, in my personal opinion, there is a couple of counterexamples to this, which are really things that you couldn't do here because you have to observe a galaxy far away that you cannot do from Earth. Then what is the outcome for the person is a major advance in how we understand things. But how many examples would you be able to mention now that go exactly in the direction where you can say a journalist, oh, this is going to be tomorrow or in 1 month or in 1... I don't know, maybe less than 5 or maybe very few. So I think we have to live with the idea that to get good results takes time, especially if you have to do it in an environment like space, where there are a lot of layers of complexity, of added complexity like vibration test, human safety, and so on and so on. One way out would be to implement many of the things that have been mentioned today here. And we are also considering in our facility definition team, maybe it's not the only one. Maybe other people will come out with smarter ideas. But I think this is why we are here. So the journalist will probably never understand this, but
that was a kind of, the question is not a good question, actually. So that's why, because when you ask what are the application, you feel guilty to say, actually, no. So then you have to explain, yes, it is related. But like you say, we don't have a lot of example. And this is fine. As long as the science behind is a good quality, and then if it is good quality, it will lead to a future application in maybe 10 years. So that's okay. Yeah. I think we have to close. Yeah.
Yes, so or on the contrary, you have many examples, but all of them indirect, right? Okay, thank you so much for this amazing discussion session. I feel like we could have spoke for another 2 hours, but I see the belly is speaking, and I will let the closing work to Pepe.
Well, it's not really closing the session. You just close the session. It's just technical information about the social dinners tonight for whoever is participating to the dinner. I sent a couple of emails with the details, again reminding you the address, the place, and the time. I heard words from the restaurant that they might actually put the tables together in one big table or not. That's unclear whether they're going to do it or not. I would recommend anyway to wait for the person who booked your table to step in. There were 3 available spots if you have anybody you want to join, but they became 2 because we already filled 1 with the suggestion from Matthias. And this was it. So thank you, everybody.
And I want to thank Olfa because she did a very excellent job in chairing the session this morning.